Now we will do an easier tuning, current loop tuning. So during the system setup portion of the class, you probably just used the automatic tuner to set up your current loop. Current loop is required for motors where you're using a direct PWM amplifier and PMAC is closing the current loop and then doing commutation and so forth. But you can also tune the current loop interactively, and there are only 3 gains involved, which makes it easier than servo loop, and the gains have a similar effect to the step move in the servo loop tuning section. So in tuning the current loop, your integral gain acts as the proportional gain acted in the servo loop, and the proportional gain in the current loop acts like the derivative gain in the servo loop. So you're essentially just doing a step move tune. The current loop tuning is part of the tuning software. So if you have the software open, you can click on the current loop tuning tab. This will only be available for motors 3 and 4 because those motors are commutated digital brush motors. And then you want to select a safe magnitude for the step. The magnitude is right here in this box. It's in these weird units of bits. Basically, that's a digital representation of a current value. A safe value for the current loop step is virtually always going to be motor x.I2t set over 5. That's right here. That is our suggested step magnitude after you have configured the I2T settings, which are a standard part of your system setup procedure. You should already have configured your motor x.IA bias and IB bias values. These are biases in the phase currents. It's important to eliminate those before you move on to the tuning. And the dwell time parameter is somewhat irrelevant. Really just depends on your inductance, how long it takes the motor's currents to rise to the target. Generally, the default dwell time is sufficient there. And then your rough phasing magnitude that shows up right here should be the same value that you're using to phase your motor. So the system setup software will have configured motor x.phaseFinding DAC for you. That's a parameter that indicates how much current to force into the phases when you're phasing. Phase finding DAC. And that's usually something like motor x.I2 t set over 2. It's generally equivalent to that value. So those are some safe reference magnitudes for you. And then you click on Do a Current Loop Step right here. And it will create something that looks quite a bit like the step move in the servo loop. So I mentioned that the current you're commanding is in these weird units called bits. If you want to convert the bits to actual amps, you can follow these equations. You don't need to memorize this. It's just a reference slide, number 150. So if you are using a DC brushless motor or any motor without a magnetization current that PMAC applies, you can use this formula, where this is the current that you're commanding from the program, and then this quantity max ADC is something you look up in your amplifier's manual. It represents the number of amps that maxes out the ADCs inside your amplifier. And then you just plug and chug, and you can see how many amps you're actually applying. And then, like I mentioned, we only have 3 gains for the current loop, which makes it a lot easier. We have the integral gain, motor x.II gain, which I said acts like a proportional gain does in the servo loop. It will basically increase the natural frequency of your current loop. And then we have the feedback proportional gain, motor x.IPB gain, and the forward path proportional gain, motor x.IPF gain. Both of these proportional gains will act as a damping effect in the current loop. So the steps for tuning the current loop are to first increase II gain until you overshoot and oscillate around the current loop target, and you want to add a little bit of damping in your proportional gain. So safe starting values for these are 0.001 in II gain, and then 1 in either IPF gain or IPB gain. And then you keep increasing your integral gain and your proportional gain until you reach the natural frequency that you desire. A good natural frequency target for most brushless motors are between 200 to 500 hertz. If you have a higher performance motor, though, like a galvanometer, then you'll probably aim for multiple kilohertz in your current loop. And then the amount that you damp really generally wants to be a lot higher than the servo loop, because if you're not damping your current loop, you could actually be creating spikes from overshoot that could fault your amplifier. So any spike in the current loop actually indicates a large temporary current spike, which can trigger I2T faults in the amplifier. So generally you want a damping ratio above 0.707. And something to note is that if you write out the closed loop equations, II gain is directly proportional to your natural frequency, and then your proportional gains are directly proportional to the damping ratio. So the tuning diagrams are the same as the servo loop. So you want to overshoot and oscillate around the target, and then damp out the response using proportional gain. If you have a response like this, you have too much proportional gain and it's too damped, so you want to decrease the proportional gain or increase the integral gain. This kind of thing means you don't have enough integral gain, so you want to increase that. You may also want to recalibrate your IA bias and IB bias if you didn't do that. And then this is the kind of response that you're looking for, where you have no overshoot and no oscillation along the target value. So the difference between IPB gain and IPF gain are explained on this slide. The main thing to remember is that if you want to keep your damping constant, and therefore also the location of the poles in your closed loop system, you want to keep the sum of these two gains the same. And then as long as you're keeping the sum constant, you can shift any amount from one to the other gain. So you can have 3 in IPF gain and 0 in IPB gain, or 1.5 in both, 1.7 and 1.3. As long as you keep the sum the same, it's fine. Now, the IPF gain and the IPB gain act on different current values. So IPF gain acts on the commanded current, so your current loop will respond more quickly to changes in command, but may actually make your current loop response noisier than the IPB gain when your command is rough. And this can actually trickle down into your servo loop and cause problems. So if you have a pretty low resolution position sensor, you should not use IPF gain, because that low resolution will get used in the current loop and will create a noisy command and cause problems. IPB gain, on the other hand, will act on your actual current. So if you have a low resolution sensor, you can use the actual current, which is just what's coming out of the motor, and this is naturally filtered by the motor's characteristics, like the inductance and so forth. So the actual current will generally always be smoother than the commanded current in the case of a low resolution sensor. it will create a smoother but slower response to changes in command. So if you want to be super safe, you can always stick with IPB gain, and you'll get a nice smooth curve. And you virtually never need to use IPF gain. But if you know what you're doing, you can use both or one or the other. And lastly, making your current loop needlessly responsive, like greater than 800 hertz, can actually cause problems in the servo loop because it's just so jittery, it will respond probably too quickly to changes. So here's an example of a pretty good step response for a brushless motor. You can see we have almost no overshoot, just about 1%. Natural frequency is greater than 250 hertz. And we go right to the target, which looks like around 1600 in this case. And we settle within 2 milliseconds. So as we practice, you can try to imitate this plot, but honestly, you can probably do a lot better. You guys, without much effort, could probably get 350 hertz with no overshoot. So let's do a little bit of hands-on. Start by opening your tuning software and then going to current loop tuning, and you'll have to select one of your commutated motors, so motor 3 or 4, and then go to the interactive tune button and start with a really safe integral gain value of 0.001 and a safe backpath proportional gain of 1, a magnitude of I2T set over 5, which in my case is 1,780. And I got that just by computing it in the terminal window. You can do the same thing I did if you want. It's just a handy trick. You write something like P1 equals motor3.I2T set over 5, P1. It will compute this value, stuff it into a variable, and then display the variable. You haven't learned what a P variable is yet, so don't worry too much about that. It's just a general purpose variable you can use for calculations. So then I take that result, 1780, and stuff it in my step magnitude and then issue the current loop step. So that looks bizarre. I'm going to check my motor status, make sure I don't have any faults. If you have a problem, I recommend keeping the motor status window open. You can get it by clicking on status right here in the toolbar, and then you can drag it to the right. And scrolling to my motor 3, I can look for any faults here. So if you're on a limit or something, like you have the limits on, you won't be able to do the current loop step and so forth.